All right. Maybe later. Oh, is it? I do not remember a single thing. But I could be wrong.
A little bit of everything. I've got a lot of funk music on my playlist right now. Not Rodgers. George Clinton. Carlton Funkadelic.
Yeah.
Dude, you're doing your homework, man. Come on. All right, guys, let's do this. What's the name? No. On your paper. Right? Where do I start? Out the alcohol card. Does it matter which way I go around the ring? Yes. Because one way will give me lower priority to that double bond than the other. Yes? 3 this way, only 2 this way. So 2, 3, 4, 5, and 6. Yes? Okay, so how do I deal with this?
3 cyclo.
Cyclo,
Hexene.
hex. If we do ene, then we're saying there's no number for that. Yes? Can't do that. It's got to be what? 3 ene,
1 or
1 O. What's another acceptable way to do this? Where does the 3 go?
at the front.
In front of cyclohexene. Yes? So you can also call this 3 cyclohexene 1 ol. 2 acceptable ways to name them. Okay? I really do believe that these ene-ols, the ones that have alkenes and alcohols, are some of the more tricky to put together. And they're really not that bad. Okay? What is my parent for the second compound? It's not benzene. What do we call benzene with an alcohol on it? Phenol. My parent is just the entire phenol. Yes?
Yes.
We would still count carbon 1 as the carbon where the alcohol is. So where is my methyl group compared to that?
2.
Okay, so I have 2 methyl phenol. That's it. Okay? We'll come back to this when we get to benzene-based compounds. Okay? Whoops. 2 methyl phenol. Okay? Yeah.
I don't know if it's possible, but if it was like a church where it would alphabetically be kind of after the phenol.
But your parent is still phenol. And the parent is always the last part of the name. Okay? And we'll come back to this when we get to benzenes, but substituted benzenes get common names a lot, which means the entire benzene ring with the alcohol is one name that gets called the parent. Okay? This is because benzene-based compounds were some of the first compounds that people started playing around with and knew about, and they got named before IUPAC came in. And so all of these benzene-based compounds got common names before the IUPAC system got put in place. Okay? What's my parent here? I agree with heptane. Yes? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yes? Which direction do I number? Right to left or left to right? Right to left in order to give preference to the alcohol. 1, 2, 3, 4, 5, 6, and 7. Everybody with me on that? Okay. So, no? Okay. 5-methyl. 3-heptanol or 5-methyl heptan 3-ol. Under the new system, right? Am I done? What am I missing? Stereochemistry. There is stereochemistry implied for the alcohol in this molecule. What's the stereochem? We positive? You sure? Priority 1 is alcohol. Priority 2 is this side or this side? Okay, so priority 2 is here. Priority 3 is, and then obviously priority 4 is the implicit hydrogen going away from us. Connectivity 1 to 2 to 3 is going counterclockwise. I agree, the stereochemistry there is S. We now have 3S, 3S, 5-methyl, or 3S, 5-methyl. We okay with this for the most part? Everyone that knows me knows we're now done with this. We have named harder stuff than you're ever going to encounter on your final or in the MCAT. So it is time to talk about real alcohol stuff, which means reactions. Actually, I'm going to go through properties again real quick just to make sure we're all good with the properties of alcohol. Okay? Now, I've already given you a hint to the properties of alcohol. And what is that? They are very much like water. Now, this does not mean that they're going to behave like water more than they do organic compounds. But what this means is their physical properties are going to be similar to the physical properties of water. Meaning that if I look at alcohols compared to alkanes, alkenes, alkynes, or alkyl halides, then alcohols are going to have higher boiling points, they're going to have higher melting points, they're going to have higher densities, higher viscosities. For what reason? I told you last time. Hydrogen bonding. Yes, the fact that an alcohol like methanol can have the hydrogen of one molecule, hydrogen bond to the oxygen of another, and then again, yes, and then again. It forms a framework of hydrogen bonding between all of the molecules. This heavy attraction between the molecules makes it harder to pull them apart. It makes them hang out closer to each other. All of that drives up all of the physical properties. So if you look at alcohols compared to other organic molecules, alcohols are going to have higher boiling points, higher densities, higher viscosities because of this hydrogen bonding scenario. Okay? What else do we know about water? Is it basic or is it acidic? It's both. Yes? If I put it in the presence of a strong acid, water is a base. If I put it in the presence of a strong base, water is an acid. We call that an I can never spell it. I think it is amphiprotic with an I. Let me make sure I can spell. Ampho with an O. Amphiprotic, or we also refer to it as amphoteric. Okay? What that means is it can be an acid or a base. How do organic chemists deal with acidity and basicity exclusively? My students, you better jump in here right now. How do I, me, deal with acidity and basicity of organic molecules? How do I determine if something's an acid or a base? pKa. I look at relative pKa values. Something with a higher pKa will tend to work as a base. Something with a lower pKa will tend to, function as an acid. So what is an alcohol, an acid, or a base, just by itself? Neither, because acidity and basicity is relative. Nothing is an acid unless I put it in the presence of something that is more basic than it is. Nothing is a base unless I put it in the presence of something more acidic than itself. A compound in and of itself is just that compound. It is neither an acid nor a base. It will not serve either of those purposes until I mix it with something else. Water, acid or base? It's neither, man. It's just water. If I mix water with KOH, then water is going to behave as an acid. But if I mix water with phosphoric acid, then water is going to behave as acidity and basicity is relative. Anything in a vacuum is not a descriptor. It is just itself. It has to have something to, yes, exchange a proton or electrons with to function as either an acid or a base. So let's look at some pKa values for alcohols. Come back to those last two in a minute. Okay, standard alcohols. And what I mean by standard alcohols is alcohols on molecules that are generally just sp3 hybridized carbon. Yes? Something like tert-butanol, isopropanol, or ethanol. Have pKa's that range between 16 and 18. Okay? They're not very acidic, but they're not extremely basic either. They kind of land in that middle zone, just like water, which is why they function as both. Yes? But if I mix this with any organic or standard acid, that alcohol is going to behave as a base. Because almost all of our organic acids, all of our standard mineral acids have pKa's that are below 5. Yes? So if I mix an alcohol with a carboxylic acid, or if I mix an alcohol with something like HBr, HCl, H2SO4, the alcohol is going to behave as a base. Okay? But in the presence of things like amines, yes? Something with nitrogen, where it is very, very, very likely to work more as a base than an acid. In fact, most amines have pKa's in the 20s. If I mix an alcohol with an amine, then that alcohol is going to behave as an acid, not as a base anymore. Okay? Also notice the tree. What would we call this alcohol? Primary, secondary, tertiary? Okay, so this is a tertiary. What's this one? Okay, secondary. What's this one? What happens to pKa's as I go from tertiary to secondary to primary? It starts to go down. Yes? And so what we see is primary alcohols is a general trend are more acidic than secondary, which are more acidic than tertiary. So the more substituted the alcohol is, the less acidic it becomes. Okay? We all understand how inductive effects influence acidity by now. If I put electron withdrawing groups on a molecule, it becomes more acidic. And it becomes more acidic for two reasons. A lot of people think of it in terms of the ability to give away a hydrogen. So by putting all these fluorines on here, they steal electrons from this carbon, which steals electrons from this carbon, which steals electrons from oxygen, which weakens the oxygen-hydrogen bond. I think of it the other way. If I lose the hydrogen off of this alcohol, if it behaves as an acid, what's the formal charge on that oxygen? If I react this with KOH, the OH minus will pull that hydrogen off, yes? Which in turn will break the oxygen-hydrogen bond heterolytically toward my oxygen. So what will the formal charge on the oxygen for the conjugate base be?
Negative.
Negative. That negative charge on the oxygen normally resides very heavily on that oxygen. But if I have fluorine out here, fluorine is stealing electrons from, which is stealing electrons from, which starts to steal electrons from the negatively charged oxygen. Those inductive groups help to stabilize the negative charge on the oxygen by pulling electrons away from it. And so, really, these inductive groups stabilize the conjugate base by pulling electrons away. And by doing that, it makes them better acids. So inductive groups will always make acids better. Also, please note, why is this fluorine alcohol more acidic than this one? Fluorines are just closer. Inductive effects work a lot like electricity. The closer to the source, the more you get. Yes? The way I explain that to people is if we join a bunch of people hand to hand, yes, let's say 40 people, all join hands, and then the person on one end grabs a live electrical wire. That person, gone. Right? The electricity at that source is so strong, that person isn't gone. But on the end, number 40, that person may be okay, because the electricity has to travel through 39 other individuals before it gets to you. The effect is weakened the further away from the source you are. Yes? Okay? It's an example. We have to push electricity to houses, yes? Or actually, maybe the internet is a better way. Anybody here a Comcast user? You don't have to self-identify. It's okay. It's okay. If you are at the intro of your neighborhood, where the internet, it goes straight from the line to your house, you get the best internet in that neighborhood. If you live at the very end of the neighborhood, that internet is going through everyone's house before it gets to yours, and by the time it gets to yours, you are not getting the same internet that the person at the beginning of the neighborhood is getting, whether you're paying the same or not. Because it is diminished as it goes down the line through all of those houses. That's why I am a fiber internet user, because it does not diminish. Light is light is light. Yes? So fiber internet is based off of light, not off of electricity or radio signals being passed through a line. Light doesn't diminish as it passes through a cable. So the person at the front gets the same internet speed that the person at the back gets. But if you are, yes, landline or cable internet, you are passing an electrical charge through an electrical wire, and that diminishes the further from the source that you are. So the closer to the source you are, the better your internet is, you're getting full speed, right? 25 blistering megabits per second. Whereas the poor bastard at the end of the neighborhood is receiving 12.5 to 18. Okay? And that is just because as we pass this through a line, it diminishes. Inductive effects of withdrawing groups are the same way. The further away from the acidic functionality, the less effect it has. The closer it is to that acidic functionality, the greater the effect. So the closer those withdrawing groups are to the alcohol, the more acidic that alcohol is going to be. Does that make sense to everybody? Okay. Here we go. One alcohol on a 6-membered ring. The pKa is 9.8. Almost half of the pKa here. Why in the hell is this 6-membered ring alcohol twice as acidic as this one? It is resonance. Resonance what though? There is no resonance here right now except for the benzene ring itself. But what happens after this behaves as an acid? What I'm left with is my deprotonated conjugate base. Yes? And it is not just resonance. It is resonance stabilization of the conjugate base that makes this more acidic. Yes? Because rather than generating a compound like this one, where all of my negative charge in my conjugate base is stuck on that oxygen, this conjugate base can distribute that negative charge across the entire framework of the molecule through resonance. What happens when we distribute a formal charge across a framework? It makes the molecule more stable because you're no longer forcing that negative charge to live in a single place. Yes? For those of you that do not see that, one lone pair comes down, forcing that bond up as a lone pair here, giving me a resonance form that looks like this. And I can distribute that negative charge again, yes? By moving this lone pair down as a double bond here and pushing it to there. By distributing that negative charge around the framework, we take what should be a very unstable conjugate base and we make that conjugate base more stable. The more stable your conjugate base is, the better the original molecule is at being an acid. And that's how we explain the difference there. Are we mildly okay with the acid-base properties of alcohols? Okay? Really, this would work the same way as my acid-base problems from last year. I give you an alcohol, I give you another compound, I show both the pKa's, you tell me which one's the acid, which one's the base, show the full reaction, arrow pushing, whole 9 yards, structure of the conjugate base, structure of the conjugate acid, all formal charges included, etc., etc. Okay. Now, there's a very good reason for talking about the properties of alcohols, especially acid-base properties of alcohols. When we made it to the last section of first semester, we saw things like this. What is that reaction? What mechanism will this reaction go through?
SN2.
What type of alkyl halide do I have?
Primary.
Strong or weak nucleophile?
Strong.
How do I know it's a strong nucleophile?
Negative formal.
Formal, negative, charge. Not just formal charge. Formal positive is not a nucleophile. But formal negatively charged atoms are strong nucleophiles. Strong nucleophile, primary alkyl halide. This is an SN2 substitution. Welcome back, everyone. It's good to see everybody. Okay, glad to be here. This will attack there, kicking off the bromine, yes, and giving me basically an ether. Plus Br minus. What is that strong nucleophile? Anybody remember the name? Methox. What do we put at the end for negatives? IDE, methoxide. Absolutely. So this is methoxide. Do we just grow it on trees? Where does it come from? Where do I get methoxide? What is methoxide? This is the conjugate base of methanol. Yes? If I deprotonate methanol, that removes the hydrogen, forces the oxygen-hydrogen bond onto the oxygen, leaving me with an oxygen that is formally negatively charged, and that is referred to as methoxide. All of these alkoxides that we used last semester as strong nucleophiles, all of them are generated by deprotonating alcohols. You remove the hydrogen from the alcohol goes from being a weak nucleophile to being a strong nucleophile because it has a formal negative charge. It's not magic, it's acid-base chemistry. By using this as an acid and removing the hydrogen, I am left with a strong nucleophile, which is the conjugate base of the original nucleophile. Okay, so how do I do it? We've already discussed that methanol probably has a pKa somewhere between 16 and 18. Yes? Somewhere around 16 to 18. That's not super acidic. So how do we deprotonate alcohols? And let's be honest, what we are really saying is, how do we form alkoxides? How do we turn alcohols into strong nucleophiles? Yes? How do we turn alcohols into strong nucleophiles? I just showed you. Deprotonate the alcohol. That's right. Thank you. Deprotonate the alcohol. By removing the hydrogen, you put a formal negative charge on the oxygen. That turns the alcohol into an alkoxide, which is a strong nucleophile. So, if I want to do that, there are a couple of reagents I can use. The most common reagent is to use something like potassium metal or sodium metal. Those metals are strongly reactive with the hydrogens on the alcohols. They will remove those, turning the hydrogen into H2, hydrogen gas, okay? And what you will generally end up with is, let's say we react it with potassium metal, okay? Then what we end up with is the potassium salt, or potassium ethoxide in this case. Yes, we all realize that O- cannot exist as O-. It has to be counterbalanced. So almost all of our oxides are alkoxide salts. They will be paired with potassium, or they will be paired with sodium, or they will be paired, yes, with one of those other group 1 metals. Okay? This is your actual alkoxide. Yes. Yes, yes they are. Thank you. It looked right in my brain. I've given you guys a couple of other very strong bases. Can anybody name one? No. Are you telling me that OH minus is stronger than OR minus? They're both what? O minus. Neither one of those is going to be stronger than the other. You're not going to get complete deprotonation of your alcohol. You may get equilibrium, right? You may have a little bit of both, but we're not looking for a little bit of both. We're looking for only this. Hydroxide is strong in terms of general chemistry, but not strong enough in terms of organic to deprotonate that alcohol. You can't do it with that. Anybody else remember? Sodium amide, I heard it somewhere. You should take credit for it. NaNH2, sodium amide. I spoiled this already because I already told you that nitrogen is more basic than oxygen. Yes? Okay? You can also do that deprotonation through the use of NaNH2. The NH2 is negatively charged. That nitrogen will remove the hydrogen, put those electrons on, and give you basically, in this case, sodium methoxide. Anybody else? Hydride reagents. H minus is a ridiculously strong base. Because what does hydrogen really want to be? Not H minus, but H2. Gas. Hydrogen gas. So by reacting this with something like butanol, the H minus will remove a hydrogen, making hydrogen gas, yes, and generate the alkoxide. There are a couple of others. We'll talk about them later. Please remember Grignard reagents. Yes, from last semester, if I react a Grignard reagent with water, it deprotonates the water. Yes, and destroys my Grignard reagent. If it'll deprotonate water, it'll deprotonate the alcohol. Yes?
So why is KOH not strong enough to deprotonate alcohol?
Because KOH has a pKa, or water has a pKa very similar to those alcohols. Oxygen minus is oxygen minus is oxygen minus. We're talking about making these as the major product. Notice these are going one way. I'm not saying that hydroxide won't deprotonate an alcohol. It will not completely deprotonate an alcohol. And if we're trying to make this to use it as a reagent, getting a 15% mixture doesn't help. Okay. Are we okay with this? How do I make alkoxides? Deprotonate an alcohol. I've given you 3 different reagents to use to do that. Okay? All right. It's in the book, I promise. If you don't have the book, that's your own damn problem. I had nothing to do with that. Everyone in here that is my student has already heard my spiel. You need a book. You just do. It doesn't have to be this one, but it needs to be a book. Reactions of alcohols. There's some good news and there is some bad news, and I bet it's the same piece of news. We already know a lot of these reactions. They are first semester reactions. Yes? But as a general guideline, if we talk about alcohols, we can turn alcohols into a number of different functional groups, or vice versa. We can turn those functional groups into alcohols. Okay? I think one that comes to mind from the end of the semester last year is halides. We learned to turn alcohols into halides, and we have already known how to turn halides into alcohols. Yes? Reaction of a primary alkyl halide with hydroxide will do an SN2 substitution, giving me a primary alcohol. Reaction of a secondary alkyl halide with hydroxide will give me an SN2 substitution and give me a secondary. Why can I not do that with tertiary? Tertiary alkyl halides are too sterically hindered. They do E2 elimination. Yes? I can also turn alcohols back and forth from ethers, as we're going to find out. Okay? We can go back and forth between alcohols and ketones. We can go back and forth between alcohols and aldehydes. We can go back and forth between alcohols and esters. We can go back and forth between alcohols and carboxylic acids. We can go back and forth. What's the only one that I've left out? You should already know it was last semester. Boo. Boo on you. Alkenes. So what we will do is we'll start with the reactivity of alcohols by talking about reactions that make alcohols. Yes, reactions that turn a molecule into an alcohol. How do we do it? I'm so glad everybody spent some time with those workshops I posted before class started. It really paid off. Oxymercuration. What are the reagents for oxymercuration? Mercury acetate in water as step 1. That forms my alcohol, but the mercury will still be attached to my molecule. So I have to do the demercuration step, yes? Which is NaBH4, sodium borohydride. I can do that exact same reaction just using acid and water, yes? But if I do that, it goes to a carbocation intermediate because it's just electrophilic addition, yes? Which means I get carbocation rearrangements, yes? And the yield is just not as good because that same reaction set of conditions goes the other way, which is called dehydration, yes? Okay. Oxymercuration is the best way to do that. Okay, BH3 and THF. Step 1. Step 2 is hydrogen peroxide and water. In base, sorry. H2O2 and OH minus. This is referred to as hydroboration. This alcohol has a regiochemical descriptor. What is that regiochemical descriptor? Markovnikov. Yes, this is a Markovnikov alcohol. This is a non-Markovnikov alcohol. Remember these two? Yes? No? Maybe? Go back and look. This is not an exclusive alcohol. We're not going to get just an alcohol. We're going to get what kind of compound? This goes through a brominium ion intermediate.
That's right.
Bromine adds cross the double bond, forming a brominium ion intermediate. That brominium ion intermediate is opened by attack at the more substituted carbon by water, which is then deprotonated, leaving me with a halohydrin. Yes, a halohydrin that looks something like this. Please note that the alcohol and the halide add anti to each other. They add anti because the brominium ion intermediate blocks one face of the molecule, forcing the, water to attack from the opposite face. Also, please note that I could draw the product this way. Equally valid. Why? Because the brominium ion can form on the top or on the bottom, leading to both of those products. Okay? Absolutely. Except we don't use the term cis, we use the term syn, S-Y-N, because we talk about the addition, not the relationship of the two compounds, the two groups to each other. So this is anti-addition. This gives me a product where both of the alcohols will be on the same face, which we call syn addition. How many new things so far? None. How do I make the transdiol? What would be my starting material to get a transdiol? I've heard a few people.
The NBS.
The epoxide. I can ring open that epoxide under either acidic or basic conditions, both of which you have mechanisms for. Full mechanisms for. Yes? By reacting this in either acidic or basic conditions, that will lead to the formation of the transdiol. You get a transdiol because the epoxide, like a brominium ion, blocks one face of the molecule. Therefore, the incoming water in the acid or the incoming hydroxide under the basic conditions attacks from the opposite face of the epoxide, leading to a product that has those alcohols trans to each other. Okay?
Dr. Houghton?
Yes?
Is this the same reaction that when the basic reaction does, then that attacks the less substituent?
Yes, it does. Spoilers, spoilers. Right? So, the question was, what if that alkene is not equally substituted? I'm sorry, the epoxide is not equally substituted. What if I start with this? Then under acidic conditions, I protonate the epoxide, and my water will attack at the more substituted carbon, because that protonated epoxide is very much like a brominium ion intermediate. So the addition of the acid protonates the epoxide. Low pair on oxygen picks up the hydrogen, forcing the electrons onto the oxygen. Yes? And what that gives me is an intermediate. Well, it looks like this. Does everyone see the similarity here between this intermediate and a brominium ion? We have one atom connected to both carbons, and that atom has a formal positive charge on it. That positive charge is distributed to the two carbons connected to it. But the more substituted carbon will accept more partial charge than the less substituted. Meaning that when my molecule of water attacks that intermediate, it will attack at the more substituted carbon. It will also attack that more substituted carbon at the opposite face of the existing epoxide, forcing the methyl group up, and so my product here will look like this. Please do not forget, this goes through one last intermediate where my alcohol is still protonated. Yes? And another molecule of water pulls that hydrogen off, giving me my product. Okay? We'll see that again in the ether chapter in a few weeks, and we'll go through the mechanism in full again. When I react that exact same molecule with base, I am now attacking a neutral nucleophile. Neutral electrophile with a strong nucleophile. This is going to attack directly at the non-protonated epoxide. Because of that, this is more SN2-like, and we know that that is, yes, limited by sterics. The higher the sterics, the less reactive. In this case, your alcohol or your hydroxide will attack the less substituted side of your epoxide, ring opening that oxygen to the more, yes, substituted. And so what we will end up with here is an intermediate, is the O minus on the top, the methyl down, the hydroxide down on this side. The O minus picks up a hydrogen from water, giving me a product that looks exactly opposite to the product that I just made. But please note, both products are trans diols. Does it matter if I have these alcohols backwards? One, yes, if I draw it this way instead of this way for the basic conditions, does it matter? Yes? I don't get both products here. My epoxide is already drawn as being on the top face of this molecule. There is no intermediate that's going to form on the top and the bottom. There is only one product for the base opening of this epoxide. That one product is that. Have we done anything new yet? No. Not at all. How we feeling, guys?
Good.
Okay, welcome back. It's all fun and games until, yes, someone doesn't remember anything from the first semester. Does everyone see why I said that if we do not have a strong background from last time, we're in trouble? And that is because all of this stuff is, yes, desperately related to all of the other material. If we don't remember something, you have to do double duty. You have to relearn Orgo 1 while learning Orgo 2. And it's going to be a steep road, folks. I recommend help, personal tutors, yes, the tutoring center, or, yeah, everybody in the village. Okay. We're going to do a few new ones now. Carbonyl compounds like carboxylic acids, ketones, and aldehydes are what we refer to as the oxidized form of alcohols. Oxidation and reduction go in opposite directions. I can reduce carbonyls to alcohols, and I can oxidize alcohols to carbonyls. So if I'm trying to make alcohols, I can take things like a ketone or an aldehyde, and I can react those with reducing agents. We are going to have two main reducing agents for carbonyls. One of these you've seen before. Which one have we seen before? Sodium borohydride NaBH4. NaBH4 is the last step of? Man, we just did this, right? Oxymercuration. What you are doing is you are using the sodium borohydride to reduce the mercury, and that is what makes the mercury fall off of the organic compound. So it is still functioning as a reducing agent. The difference between these two is this is a strong and this is a weak. Okay? Both will work on either ketones or aldehydes. So if I use either of those two, as step one, second step is just a water rinse. So basically you mix the sodium borohydride in with the alcohol, you let it stir for a little bit, then you take a beaker of water and you pour it in. That's all a water rinse means, okay? And all you are doing with that is killing the rest of this, getting rid of any excess reagent, and reprotonating the oxygen to turn it into a secondary alcohol. So ketones reduce to secondary alcohols. What's the aldehyde going to reduce to? A primary alcohol. Same conditions. Lithium aluminum hydride or sodium borohydride. Second step is a water rinse. So fill in the following statement. Ketones reduced to blank alcohols. Aldehydes reduced to primary alcohols. And you may use either your strong or your weak. And we're going to talk about the differences between the two in a minute, why you would keep both, why you would, yes, have one and not the other. Okay? But, first and foremost, let's talk about the other reductions that we can do with these reagents.
It's 2 minutes.
Guys, you're going to have to help me out. I can barely hear my own brain when you're not talking about me behind my back. What's the difference between the reduction of this acid and the reduction of my ketone and my aldehyde? Did I put both reagents there? Which reagent did I put? Only the strong one. Esters and acids cannot be reduced by sodium borohydride. They can only be reduced by lithium aluminum hydride. Okay? And what we will end up here is this bond will be broken. The OH of the carboxylic acid will turn into a molecule of water, and this carbonyl oxygen will be turned into an alcohol. And so what we end up with is this alcohol and a molecule of water. You're going to get a mechanism for this reaction, but you're not going to get the mechanism for this reaction until we get to the carbonyl section of this book, which will be for your 4th exam, more than likely. Okay? So no mechanism for now. You just need to know what you get. Same thing here. No mechanism yet, but we will get one later. If instead of a carboxylic acid, the compound is an ester, I will still do the same thing. But notice, this is not OH. So it's not going to turn into water. It's going to turn into a second alcohol. So the reduction of esters gives me the formation of 2 different alcohols. Okay? So if I treat this with lithium aluminum hydride and a water rinse, I still get that alcohol, but now I will also get a molecule of ethanol. You are still breaking that molecule right there. Does everybody see that? Then all you are doing is removing your pi bond here, turning that oxygen into an alcohol, and turning this oxygen into an alcohol. So here's my question. Ketones and aldehydes can be reduced by either lithium aluminum hydride, sodium borohydride. Esters can only be reduced by lithium aluminum hydride. So why don't I just use lithium aluminum hydride all the time? Why bother with sodium borohydride? We always go to the money. Money's good, but let's assume that they cost the same. What do we know about things that are more reactive? They are less stable. Lithium aluminum hydride is more dangerous for one. It is more likely to catch fire in the presence of water. Okay? I have seen people set garbage cans on fire because they spill a little bit of lithium aluminum hydride and then just decide to sweep it in the garbage can. What is the humidity in the southeastern United States at any given point in time? Like 182%, right? There's a stupid amount of moisture in the atmosphere here. So what happens is that lithium aluminum hydride sits, am I out of time?
Yes.
Fine. I'll see you next time.